After electromagnetic waves, the next unit is sixth unit, that's optics. We will do electromagnetic waves after optics. So optics can be broadly divided into two parts. The one is wave optics. So we're basically starting book 2 of NCERT. This is wave optics. And another is ray optics. So you have wave optics as well as ray optics. So in wave optics, we have four topics. The first one is the concept of wavefront. The concept of wavefront. The second is the concept of interference. Third one is diffraction. Yeah, yes, Jubana, this is in school syllabus. There's one more topic which is polarization and Doppler's effect. Yeah, this is book 2 of NCERT. This year, polarization is removed, so it's not a part of syllabus for this year, neither Doppler's effect. But these three are part of syllabus: wavefront, interference, and diffraction. First, we will do wave optics, then we will come to ray optics. Now let's start with the concept of first chapter of wave optics, which is the concept of wavefront and Heinz principle. Wavefront and Heinz principle. See, what is wavefront? And before starting wavefront, the introduction of this chapter. So initially, the light was, whenever, okay, whatever you have around you, you can divide those things into two parts. They are either particle or they are wave. If I'm taking this pen is a particle. But if you talk about sound, sound is a wave. So you can classify everything in these two broad categories. That's either a particle or a wave. But the light shows the characteristics of both particle as well as wave. Initially, like during the time of Newton, Newton considered light as a stream of particles. Newton gave a theory which is known as corpuscular theory of light. Corpuscular theory basically says that light consists of a stream of particles which travels in a straight line. So that was corpuscular theory of Newton, that light always travels in a straight line and it consists of stream of particles. Up to Newton, the all prominent theories of light assume that light consists of stream of particles, the corpuscular theory. The first theory in the favor of wave characteristic of light was given by Heinz. That was Heinz theory. So Heinz was the first person who introduced light as a wave. He explained all characteristics of light on the basis of his wave theory. And Heinz theory is based on the concept of wavefront. So Heinz theory is a beautiful theory. It just consists of geometry, nothing else. In Heinz theory, there are no equations, no formula, nothing. They are just geometrical constructions. Using those geometrical constructions, you can prove various characteristics of wave or various properties of wave. Various wave light phenomena which light shows, like using this, you can explain reflection, you can explain diffraction, you can explain polarization, interference, everything. So we are not doing corpuscular theory. We will do Heinz theory, the first theory which favors light as a wave. Now, this Heinz theory starts with the concept of wavefront. So let's see what are wavefronts. Technically, wavefronts are continuous locus of points. The definition of wavefront is they are continuous locus of points which are vibrating in same phase. This is the definition of wavefront. So wavefront basically is, say you have a source of light. This is source of light. From this source, light propagates in the forward direction. From this source, light propagates in the forward direction in the form of wavefront. In the forward direction, the light is propagating in the form of wavefront. Source generate first wavefront, then this wavefront will generate second, then the second wavefront will generate third, and so on. This is how light propagates in the form of wavefront. Mathematically, wavefront is, say you have a source. This source will generate some disturbances. So I'm taking all disturbances which are at a fixed distance from the source. So the combination of all disturbances which are at a fixed distance from the source are known as wavefront. To understand wavefront, I'm just showing you an animation. That animation will clear the concept of it. So we have to study wavefront for light waves, but to understand wavefront, we are taking case of sound, basically waves in a water. This is a pond, a water surface, which is calm. There are no disturbances. You can compare this as with a room where there is no light source. A completely dark room is comparable to this thing. So you have a water surface with no disturbances. This is a stone. This stone is basically the source of disturbance. You drop this stone
in a still water.
In this water. So this stone is basically the source of disturbance. When you drop this stone into it, this stone will generate a wavefront. It will basically generate some disturbances. So all these disturbances which are at a fixed distance r from the stone is known as wavefront. So the stone generated first wavefront, the first wavefront will generate second, second will generate third, and this way, these water waves will travel. Just like water waves, light waves can travel in the form of wave. For the light waves, instead of stone, you have a source of light that could be a bulb. Just like this stone generate these water waves or the wavefront in water, that bulb will generate wavefronts of light. If your stone is just a point mass, then these wavefronts are spherical. If your light source is a bulb, is a point-sized bulb, then the wavefront would be spherical. So these are basically wavefronts which we have to study. The thing is, you can see wavefronts for water waves, but you cannot see wavefronts in light waves. You basically, what you see is the ray, the direction in which light is traveling. So is it clear what is wavefront? These disturbances are basically wavefront. Light is traveling in the form of these wavefronts. So wavefront are basically the locus of all the points which are vibrating in same phase. Like this is source. I take all points at fixed distance from the source, and I call all the combination of these all points as wavefronts. Now vibrating in same phase. Mathematically, phase is the argument of sine term, but physically phase means if you take the case of a water surface. This is water surface. I dropped a stone here. All these points are at the same distance from the water surface. In these points, there would be some points which are vibrating outwards. Some points are vibrating inwards. So the points which are vibrating outwards are in same phase, and the points which are vibrating inwards are in different phases. So when I say choose points in the same phase, that means I am choosing either the points which are coming outwards or the points which are going inwards. So this combination is known as wavefront. After the concept of wavefront, we have types of wavefront. Depending upon the type of source, we can have many types of wavefront. The first one is spherical wavefront. The first one is basically your spherical wavefront. So if your source is a point, if your light source is a point, then all points which are at same distance from this light source will make a sphere. So for spherical wavefronts are for point source. So if you have a point, then all points which are, this is your source, this is your light source. Then points at equal distance from the light source will make this wavefront. Spherical wavefront. These are spherical wavefronts. So this is first wavefront, this is second wavefront. Now, if you want to draw rays, remember that rays are perpendicular to wavefront. Rays, light rays are basically perpendicular to wavefront. There's one more thing. Light energy travels in the direction of rays. So light energy basically travels perpendicular to wavefront. It travels in the direction of waves. So this is the direction in which your light energy travels. So if this is a wavefront, this is the direction of rays. These are rays. Rays are perpendicular to wavefront. So these are rays. So these are rays for a point source. Instead of point source, if you have a line source, like you have a tube light, then your wavefront is not spherical, then your wavefront is cylindrical. These are rays over here. These are rays. Rays are perpendicular to wavefront. Cylindrical wavefront. So if your light source is a line source, like a tube light, then your wavefront will be cylindrical. This is for a line source. So if you have a line source, this is a line source. Then the shape of the wavefront is cylindrical. So the wavefront is cylindrical. So for line source, this is the wavefront, cylindrical wavefront. Now, if you want to draw rays, then these are the rays. Just draw perpendicular to the wavefront. All these are rays. Light energy basically travels in the direction of rays. Okay, just tell me one thing. If your object is at infinity, your light source is at infinity, then what type of rays will you get? Your rays would be converging, you will get diverging rays, or you will get parallel rays. If your light source is at infinity, what type of rays would you get? Converging, diverging, or parallel rays? Resham, Jabana. If your source is at infinity, then the rays are parallel. If your source is at infinity, that means the rays are coming parallel. Because parallel rays meets at infinity. And
So this is in every case, in every wavefront.
in every wavefront. If your source is far away, it's a very far away source, then the rays are parallel rays are coming. This concept of rays we can extend to wavefront, plane wavefront. So if your source is very, very far away, for a distant source, like from the observer, if your source is placed at a very large distance, for a distant source, a part of spherical or cylindrical wavefront will appear as plane. So if you have a distant source, a source which is at a very large distance, a part of spherical or cylindrical wavefront will appear as plane. That means if your source is at a very large distance, then your wavefront would be very large. So this is the source, the point source, and observer is here. So the wavefront which is reaching this observer is very large. And if observer observe a part of the spherical wavefront, this small portion of the spherical wavefront will appear as plane. It will not appear as spherical. It will rather appear as plane. So that's why we call this as a plane wavefront. It's like Earth. Earth is spherical. But if you step outside and look at the ground, it appears as plane. It appears as flat. The same thing is for a distant source. If you have a point source, but the observer is very far away. So for observer, this is the distant source. Wavefront is spherical, but the observer will observe only a small portion of the wavefront, and that small portion will appear as plane. Instead of point source, if you have a line source, then again the cylindrical wavefront is very large. The portion of the wavefront which is visible to the observer is very small, and that is plane. So that's a plane wave. So this is it. We draw plane wavefront in this way. This is how we draw plane wavefront. This is a plane wavefront. Rays are perpendicular to the plane wavefront. Rays are always perpendicular to the plane wavefront. These are the rays. So all rays are parallel. This is a plane wavefront for a distant source. Then you can have converging wavefront. We draw converging wavefronts like this. These are converging wavefronts. So if I draw rays, rays are basically perpendicular to these wavefronts. If you look at rays, then these rays are converging. That's why we call these type of wavefronts as converging wavefronts. The last type of wavefronts are diverging wavefronts. Diverging wavefront. This is how we draw diverging wavefront. These are diverging wavefronts. If I draw normal to these wavefronts in the forward direction, then it's very clear that all these rays are diverging. So these are 5 types of wavefront that one should know. Spherical wavefront for a point source, cylindrical wavefront for a line source, plane wavefront for a distant source. If source is placed at a very large distance from the observer, then you can have diverging and converging wave. So you know what are wavefronts. The next thing is you need a law or a principle that tells you how these wavefronts propagate. Like we know that if you have a point source, that point source will generate a spherical wavefront. But how that wavefront will propagate through a certain medium. So for that thing, we need Heinz principle. It tells how a wavefront propagate through a medium. Propagate through a medium. So how a wavefront propagate through a medium is given by Heinz principle. So according to Heinz principle, so I'm dividing this principle into points. First point, if you have a source, then that source will generate a first wavefront, which is known as primary. Depending upon the type of the source, if that source is a point source, then your wavefront is spherical. If your source is a line source, then that wavefront is cylindrical. Source of light will generate a primary wavefront. That's the first wavefront that source will generate. Primary wavefront. Now, this primary wavefront will generate next wavefront. So every point on primary wavefront will act as a fresh source of disturbance, which travel in all directions with speed of light known as secondary wavelets. So I'm drawing it point by point. So this is your source. Your source will generate first wavefront, primary wavefront. This is your first wavefront, which is known as primary wavefront. So this primary wavefront is a spherical wavefront if your source is point source. But if your source is a line source, then this is a cylindrical wavefront. I'm not drawing the full wavefront. I'm just showing how the light will propagate in this direction. If I draw the complete circle, then I'm just repeating the same thing. I'm showing that how light travel in the forward direction, also in the left side direction. So I'm just taking a portion of the sphere. So this is the first point. Source will generate a primary wavefront. Now, every point on the source will act as a fresh source. Every point on the primary wavefront will act as a fresh source of disturbance. So each and every point on the primary wavefront will act as a fresh source of disturbance. Each point will act as a fresh source of disturbance. So every point is acting as a source itself. So source generated first wavefront, which is primary wavefront. Every point on the primary wavefront is acting as another sources. These sources will generate some disturbances, which are known as secondary wavelets. These are secondary wavelets. Secondary wavelets travel with the speed of light. So in time t, the distance that they travel is c into t. Distance is speed multiplied by time. Speed of light is c, time is t. So the distance that these secondary wavelets travel is ct. That's the second point. Third point says a tangential surface on these secondary wavelets in forward direction is secondary wavefront. So a tangential surface which is touching these secondary wavelets in the forward direction is known as secondary wavefront. So if I draw a tangential surface touching all these secondary wavelets is known as secondary wavefront. And drawing this secondary wavefront means your light waves had traveled from here to here. Your light waves were here at t equal to 0. After some time t, your light waves are here. They have traveled a distance ct. Then, for the further propagation, you can consider this secondary wavefront as the primary. Every point over this wavefront will act as a fresh source. Then you can draw another tangent, then other wavelets, and everything. So this is how light propagate in a medium in the form of wavefront. Source will generate just one wavefront. These wavefronts will keep on generating other wavefronts. There's just one more thing. I'm just adding one more thing. See, you can geometrically you can draw a tangential surface here also, means in the backward direction. But Heinz principle doesn't allow you to draw a backward tangent. The answer is light energy does not travel in backward direction. Light energy travels in forward direction. That's why we don't draw this backward tangent. Some people say this is one of the limitations of Heinz principle. Backward tangents are not allowed. The simple reason is light energy cannot travel in backward direction. Light energy does not travel in backward direction. Light energy always travel in forward direction. It does not travel in backward direction. This is it. So that is the only theory in this chapter. That's Heinz principle. Just using this Heinz principle, you can prove all laws of reflection and refraction. So let's start questions. Whatever you have studied in ray optics, like Snell's law, the law of reflection, the fact that convex lens converge and concave lens diverge, and the deviation in prism, everything that can be proved using this simple Heinz principle. There's 3 steps. Using these 3 steps, you can prove all laws. So is it clear?
Yes, sir.
Okay, so let's move on to the next slide. Resham, you have written this?
Yes, sir.
The next is start with a simple question. Discuss behavior So I incident a plane wavefront here. This is a plane wavefront that I incident on one face of the prism. This is incident wavefront. Consider this incident wavefront as a primary wavefront. From this primary wavefront, you have to draw secondary wavefront. To draw secondary wavefront, you have to use this Heinz principle. This is the wavefront which is given. To draw this wavefront, take some points on the primary wavefront. Those points will act as a source, fresh source. So I'm taking 2 points, one here, another here. This is acting as a fresh source. Then I need to draw these secondary wavelets. The radius of secondary wavelets is speed of light multiplied by time. The case that I have considered here, throughout this space, the medium is air or vacuum. That's why the speed is same. But if you consider this case, the light will travel in air as well as in glass. If I say this is my point A, and if I consider this as point B, the light waves which are moving from this point B will cover a large distance in glass, or will travel in glass for a larger portion of time, and the rays which are coming from point A, they will travel in glass for a comparative shorter period of time. This will travel distance in glass for a larger period of time, and this is comparative shorter period of time. Okay, so can you tell me the speed of light is greater in air or in glass? Speed of light is greater in air or in glass? Yeah, the speed of light is greater in air. In glass, speed of light decreases, usually decreases, it's less than air. So the wavelet that you draw from point A will have greater radius because it's traveling through air for most of the time. So its radius is large. Just one more thing. See, instead of drawing complete circle, I'm just taking this arc. Because if you look at this thing carefully, all these constructions are bases. You don't actually need these constructions. What you need is basically this thing only to draw tangent. You just need this much of arc to draw the tangent. So I'm not drawing the complete sphere. I'm just taking that arc so that I can draw the tangent. Similarly, if I take point B, so the waves from point B will travel for a larger period of time in glass. So their radius is comparatively. So they will go through a comparatively radius. So here radius is large, here radius small. So these are two wavelets. For the secondary wavefront, we can draw tangents over them. We can draw tangents over them. This is it. This is your wavefront when it passes through the prism. It gets deviated. Or I can take it to be large. These all are freehand drawings, okay? So this gets deviated. Now, if you want to draw rays, rays are perpendicular to wavefront. So these are the rays. These are the rays. These are the rays. Rays are perpendicular to the wavefront. These are the rays. So these are the rays. Rays are perpendicular to the wavefront. So it's very clear that through the prism, the rays gets bent. They gets deviated. When the rays passes through the prism, they gets deviated. This is the deviation in rays when they pass through the prism. So this is the prism. So this is the entire process, but you can use certain shortcuts. If you know your physics, then you can use the shortcuts. If you know that the prism always deviates rays, it always deviates wavefront, then just draw your primary wavefront. This is straight. Then you should know that your secondary wavefront will get deviated. Draw this thing first, then put these arcs, and then these rays. This will save time. Okay, for the next, I will use some direct concept, that convex lens. If you have to draw wavefront for a convex lens, then you should know that convex lens is converging. I will use shortcuts from now onwards. I will not use the entire Heinz principle. I'm just use some shortcuts. You know that convex lens is converging. So if you have a plane wavefront, you insert a plane wavefront on the convex lens, it gets converged. Concave lens is diverging. Okay. Convex mirror is diverging again. And concave mirror is again converging. See, Giovanna, what I did, this is my primary wavefront. I take 2 points on the primary wavefront. From this primary wavefront, I take these arcs. These arcs are basically secondary wavelets. One arc from point A, another arc from point B. Arc from point A have larger radius as compared to arc from point B. The reason is from point B, ray will travel through glass. A major distance they will travel through glass. In glass, speed of light is less. So this is speed of light multiplied by time. That's why the radius of the wavelets from point B is less and the radius of wavelet from point A is greater. I draw these two wavelets. These arcs are basically your wavelets.
Okay,
When I
sir.
draw a tangential surface over these wavelets, this tangential surface is your secondary wavelet. These red lines are representing rays. Yes, Joanna.
Okay, so clear, sir.
Now, for all these four cases like convex lens, concave lens, convex mirror, concave mirror, I will not use the complete Heinz principle. We'll do this thing using shortcut tricks. For shortcut tricks, you should remember that convex lens is converging, concave lens is diverging, convex mirror is diverging, and concave mirror is converging. So I'll use shortcut methods for the rest. Second one. So if you want convex lens, so this is the convex lens. So this is the primary wavefront. Now, you know that convex lens is converging. Convex lens is converging. So when this primary wavefront will pass through this convex lens, it should get converged. Now see how your converging wavefronts look. This is your converging wavefront. This is your converging wavefront. So when this wavefront passes through convex lens, it gets converged. So just draw this converging wavefront directly. If you know your physics, then you can save some time in this type of question. Just draw this converging wavefront. Then you obviously need some arcs. Just draw some random arcs. These arcs will basically represent your secondary wavelets. Now, can you explain why the radius of this arc is greater than this arc? I'm taking 3 points here. Why the radius of
So because
arc?
it passed without deviation.
No.
Because the area is larger at B compared to
Yeah, because the area is larger at B. The waves which are coming from B will cover a larger uh, air, distance in glass. In glass, speed of light is less than air. So the rays which are moving from point B will travel through glass for a comparative larger period of time than point A, than the waves coming from point A. So that's why. Here the speed is less, so the radius is less. Here speed is large, so the radius is large. Okay, Resham?
Yes, sir.
The reason is same, which was for here. This have lesser radius than this thing. So the reason it's the waves from this point B is covering a major time in glass than this one. Then you can always draw rays. Rays are perpendicular to wavefront. So this is one ray. This is another ray. This is third ray. The converging thing. So rays will converge. This will converge. These are parallel rays. These rays are converging. This is convex lens. Similarly, you can draw it for any type of lens. The third is for concave lens. You know that concave lens is diverging. So I take a concave lens. This is a concave lens. This is a plane wavefront. When this plane wavefront passes through this convex lens, it gets diverged. So this is the diverging wavefront. Next, you want rays, wavelets. Just draw these arcs. These arcs are basically your secondary wavelets. Now see, the waves from this point B as compared to A, the waves from point B will travel through glass for a shorter period of time. That's why the radius is large, but from A, they are moving through glass for a comparative larger period of time. So that's why the radius from point A, radius of wavelet from point A is less than the radius of wavelet from point B. Next, you can always draw rays. Rays are just perpendicular to wavefronts. So if your wavefront diverge, then your rays will also diverge. These are your diverging rays. After concave lens, the next was convex mirror and then concave mirror. It's convex mirror. Convex mirror is a diverging mirror. So if you have a convex mirror, this is the shape of convex mirror. This is polishing. So if this is the wavefront, this is the wavefront. So the convex mirror is diverging, so it will diverge. This is the shape of a diverging wavefront. This is the shape of a diverging wavefront, right? This is diverging wavefront, the way we draw it for convex mirror, concave lens. This is diverging. You can draw arcs because after reflection from the mirror, these are yours wavelets. Next, you can draw rays. It's very rare that someone asks you to draw behavior for a mirror, but that is an extreme case. These are your rays, incident rays. These are your incident rays. And these are your reflected rays. These are your reflected rays. These are the reflected rays. So convex mirror basically diverges the rays. After convex mirror, the next is concave mirror. Concave mirror is converging. So this is your concave mirror. This is your plane wavefront. So this will converge basically. So this is your converging wavefront. These are the wavelets. Next, you can draw rays. These are incident rays. These are the incident rays. So they converge at a point. So this is primary wavefront and this is your secondary wavefront. So that was the first question that one can get on this wavefront. Next, we have two more types of questions. One is you may be asked to prove the laws of refraction, basically Snell's law, using the Heinz principle. And another is to prove laws of reflection, that angle of incidence is equal to angle of reflection using Heinz theory. So let's start with the laws of reflection. Reflection on the basis of Heinz theory. Reflection on basis of Heinz theory. It's a very small chapter, just one more topic left, that is refraction on the basis of Heinz theory. So this is your mirror. This is the mirror. And this is your primary wavefront. I call this primary wavefront as your incident wavefront. Incident wavefront. Now you have to draw your reflected wavefront. And this is the mirror, M1, M2. This is your mirror. Now you're supposed to draw your reflected wavefront. The angle between the incident wavefront and the mirror is known as angle of incidence. This is angle of incidence. This is angle of incidence. Now you need to draw reflected wavefront. To draw reflected wavefront, you can use the same Heinz principle. Take 2 points on the primary wavefront. This is point A, this is point B. From point A, take one arc, or from point B, take an arc. This is the arc. The radius of the arc is speed of light into time. So that's V into T. This is the radius of arc. From A, take another arc. The radius would be same because medium is same. So both the arcs will have same radius. I draw another arc. Then finally, I draw a tangential surface. I'm drawing a tangential surface here. Tangential surface. So This is one. This is second. The radius of both the arc is same because medium is not changing, medium is same. Next, we can draw rays. So this is your reflected wavefront. This one is yours reflected wavefront. This is reflected wavefront. This next thing is you have to draw rays. So to draw rays, rays are always perpendicular to the wavefront. So this is one ray. This is another ray. So these both these rays are perpendicular to your primary wavefront. So these are your incident rays. Both these rays are incident rays because they are perpendicular to your primary wavefront. And this distance from here to here is yours Vt. This is V into T. Next, we need reflected rays. Reflected rays are perpendicular to reflected wavefront. I'm using another color. So these rays which are perpendicular, to your reflected wavefront will actually represent this one and this one. These blue color rays are reflected rays. Reflected rays. I'm just taking this. So this is incident rays. The radius of both the rays is same. The radius of both the wavelets is same. It's V into T, V into T. This is again V into T. This is also Vt. So this AB here is an incident wavefront. I call this point as A prime and I call this point as B prime. This A prime, B prime is basically a reflected wavefront. This angle here, we represent it by R. This is angle of reflection. This is angle of reflection. Here, this A prime is exactly equal to B prime, which is equal to V into T. This is basically the radius of the wavelet. So you just have to prove that this I and R are equal. To prove that this I and R are equal, you can show that A prime, this right angle triangle, and this B prime and A prime are congruent. You just have to prove that these two triangles are congruent. So in triangle, I'm taking these two triangles. BA, I'm taking this point as A. This is A. BA prime. And triangle B prime, A prime. You have to prove that these two triangles are congruent. See, BA is equal to B prime, A prime. BA is equal to B prime, A prime, which is equal to VT. Is it done? Not BA. B prime is equal to A prime. B prime is equal to A prime. B into B prime is exactly equal to A into A prime, which is equal to VT. That's my first equation. Similarly, here B A prime, that's the common side. It's side common to both the triangles. So you can say that BA prime is equal to BA prime. Third thing, angle A is 90 degree, angle B prime is 90 degrees. So you can write that angle A is equal to angle B prime equal to 90 degree. So all these three things shows that triangles BAA prime and triangle BBB prime are congruent. So triangle BAA prime is congruent to triangle BB prime A prime. Now, if triangles are congruent, that means corresponding sides are equal and corresponding angles are equal. That means I will be equal to R. So this is what you were supposed to prove, that angle of incidence is equal to angle of reflection. That's law of reflection. There is one more law of reflection which says that all wavefronts lie in same plane. So this is incident ray, this is reflected ray. I need one more ray which is normal. So I'm using this color. This is normal. This is normal. This is normal. Now, since incident ray and refracted ray lie in same plane, both rays are in same plane. So the normal to these rays means this incident wavefront and reflected wavefront will also lie in same plane. That's the second law of reflection. Now, since incident and refracted rays, sorry, not refracted, reflected rays lie in same plane, normal to them that is reflected and incident wavefront will also lie in same plane. Will also lie in same plane. This is the law of reflection. The first law, the second law of reflection. So just by drawing this diagram, you can prove that the incident and reflected angles are equal. So angle of incidence is equal to angle of reflection. That's the first law of reflection. Now this incident and reflected rays lie in same plane. So the normal to these rays, wavefronts are normal to the rays. So if rays are in same plane, then the normal to the rays, which are basically wavefronts, will also lie in same plane. So this is the interface which separates two medium. Medium 1 and medium 2. The refractive index of medium 1 is N1. The refractive index of medium 2 is N2. So basically you have to prove Snell's law here. Sin I by sin R is N2 by N1. So this is the incident wavefront. Now, this refraction could be from rarer to denser medium, or it could be from denser to rarer. So I'm proving it for rarer to denser. Maybe in exam, someone asks you to prove this thing for denser to rarer medium. The only difference is the relation between angle of incidence and angle of refraction. For rarer to denser, this is angle of incidence. This is the incident wavefront. This is your incident wavefront. For refracted wavefront, the refracted wavefront should be in second medium, because then only your light will refract. So for refracted wavefront, again the same method. Take 2 points on the incident wavefront, call one as A, another as B. From point A, take one arc. This is arc. The radius of the arc is basically V1 into T, because the speed of light in medium 1 is V1. Here mediums are changing. So when medium change, speed change. In this medium, speed is V1. So V1 is speed of light in medium 1. N1 is refractive index of medium. The refractive index of medium 1 is N1. Now, when you draw the wavefront in another medium, now in this second medium, speed of light is V2. In denser medium, speed of light will decrease. V2 is speed of light in medium 2. And N2 is refractive index of medium 2. Now, so if light is traveling from rarer to denser medium, then its speed should decrease. V2 should be less than V1. This is the only difference in the calculation. So I'm taking refraction from rarer to denser medium. If someone asks you to repeat the calculation for denser to rarer, then V2 will be greater than V1. So you take another arc. Obviously, the radius of arc would be less, because in second medium speed is less, and then you draw this tangent. This is your refracted wave, and this is your angle of refraction. So this is angle of refraction. This is angle of incidence. The radius of the wavelet here is V2 into T, because in second medium, the speed of light is V2. Now, you have to draw rays. So to draw rays, just draw normal. So this is the first ray, incident ray. This is again the incident ray. This is the incident ray. Next, you have to draw the refracted ray. First, draw normal. This is the normal. This is the normal. So to draw refracted ray, you need to draw the normal over this refracted wavefront. So I'm drawing a normal over this refracted wavefront. This is the normal over this wavefront. This is the normal over the wavefront. So these two rays that I'm drawing using red color, these are your incident rays. And the rays that I'm drawing with blue color are basically yours refracted rays. And this one is yours refracted wavefront. Refracted wavefront. This angle is 90 degree. This is also 90 degree. This is normal. This is again normal. Now you have to prove that sin I by sin R is N2 by N1. Simple calculation. Just one more thing. This whole distance is basically this thing. This is the radius of your wavelet, which is this thing, V1t. And this is this one, is the radius of wavelet in second medium, which is V2t. So I call this point as A prime, and I'm calling this point as B prime. Now you just have to prove Snell's law. That means sin I by sin R is N2 by N1. So to prove Snell's law, I'm taking these two triangles, BA prime and BA prime B prime. So I'm taking these two triangles. In triangle BA prime, BA prime. In this triangle, I write sin I is perpendicular by base. Perpendicular is AA prime. I'm sorry, this is hypotenuse, which is BA prime. So that's AA prime by BA prime. It's AA prime divided by BA prime. So how much is AA prime? AA prime is V1t divided by BA prime. It's V1t divided by BA prime. That's my first equation. This is sin I. Similarly, for sin R, you can use this triangle, which is BA prime B prime. BA prime B prime. From here, you can calculate your sin R. Your sin R is, it's perpendicular over hypotenuse. So perpendicular is BB prime, hypotenuse is BA prime. BB prime over BA prime. So your BB prime is V2t divided by BA prime, it's equation 2. Just take ratio. Sin I over sin R is V1t over BA prime divided by V2t over BA prime. So gets cancelled out. T gets cancelled out with this T. So we are left with sin I over sin R is V1 over V2. I call this as equation number 3. Now, using this ratio of speed of light, we can write this in terms of refractive index. This is the definition of refractive index. Refractive index of medium 2 with respect to medium 1, which is represented by N21, is basically the ratio of speed of light in medium 1 by speed of light in medium 2. This is the definition of refractive index. Refractive index is the ratio of speed of light. This is equation number 4. Now I can substitute 4 in 3. So if I substitute 4 in 3, then I would get sin I by sin R as N21. This is Snell's law. That's the first law of refraction. You can prove another law. See, this is incident ray, this is your refracted ray, and this is your normal. Your incident ray, refracted ray, and normal all lie in same plane. So the normal to these rays means your incident wavefront and your refracted wavefront will also lie in same plane. Now, since incident, refracted, and normal rays lie in same plane, so normal to them that is incident and refracted wavefront and refracted wavefront will also lie in same plane. They will also lie in same plane. Okay, just note it down. So from the same calculations, we can also prove that frequency does not change in refraction. So that's the last question that can be asked on basis of Heinz principle. Frequency of light does not change in refraction. When light refracts, its frequency does not change. So to prove this, you can use the fact that this radius of wavelet is basically the wavelength in Heinz theory. In Heinz theory, the wavelength is this thing. This V1t is wavelength, this V2t is wavelength. So you can write that your lambda 1 is V1t. That's my first equation. Wavelength in another medium, lambda 2 is V2t. That's my second equation. So if I take the ratio lambda 1 by lambda 2, I get V1t is equal to V2t. This will get cancelled out. I can write this as, if I cross multiply them, then this is V2 by lambda 2 is V1 by lambda. V by lambda, speed divided by wavelength, is basically frequency. So this shows that frequency does not change during refraction. This is frequency in medium 2. This is frequency of light in medium 2. And this is the frequency of light in medium 1. So that's it. This is it. So that's all about wavefront and Heinz principle. That's the first chapter of Wavefront.